participants on the Zoom here.
All right, we're good.
Ready to start?
Yep.
Do we have all? Okay. You guys can hear me clear? Okay. Hello, everyone. Good evening and happy Friday here. So welcome to the Math Kangaroo session here, the live session. I would like to introduce myself here. I'm the co-host here, Kanchana Perumala. I'm from Michigan. So I'm kind of facilitating the Math Kangaroo competitions from past 8+ years. And I do have a lot of kids here to, especially the elementary kids who would love to understand a little bit more on the math, how to solve these Math Kangaroo word problems and all. So we normally host some workshops for them to help them out to break down those little kids to be prepared for the competition that happens in March timeframe. I do have two girls, both are in high school. One is freshman and the other one is sophomore. So they used to participate in Math Kangaroo from past 7+8 years. But fortunately this year they kind of said they're gonna do it like as a more voluntary and hosted the whole event last week in the March. So they helped me out to run the whole, hosting the whole Math Kangaroo and even proctoring the center as well. So they are pretty much fond of math and they really had fun be part of this Math Kangaroo organization. So most of you have already participated in our competition this year, and you are one of the 3.5 million students registered this year, and hope you all did really wonderful job in there. Math Kangaroo doesn't not only host the competitions every year, but it also offers like a group and private lessons and webinars and a lot of online math learning resources as well, as we have right now these live challenge kind of sessions. So please visit the website mathkangaroo.org to find more information. So now I would like to introduce our co-host from Daily Challenge, which is Eddie and Evan. So they both are going to take care of the session from here on. So I just want to give a little more introduction about Eddie here. Just raise your hand.
Hello.
Thank you. So Ed is from Ohio State Math Counts. He's a Math Counts champion and has been coaching the middle school Math Count team for 2 years. And he also has a passion for a lot of languages here. So his passion for language learning and international cultures. So he is a fluent in Mandarin, Shanghainese, conversational in Spanish, and learning Japanese. So welcome, Eddie, for this session here. Thank you. Thanks for doing this for the kids here. So the second co-host that we have here is Evan. Okay, if you can raise your hand. Yep, thank you. Evan is from Nevada State Math Count champion. He has a qualifier for USA GMO in 2022. He has qualified for AIME since 7th grade and is also co-president of his school's math club. So apart from math, he enjoys skiing, learning about aviation, and following the St. Louis Blues, viola, and the best part is he loves eating bread. So you're in a good hands right now. They're both gonna help you out the whole session here and help you in the rest of the 1 hour. So hope you all enjoy the session. So you both can take it over from here.
Perfect. Thank you for the introduction. Really happy to see so many guys here. We're going to be going over the Math Kangaroo grade 7 to 8 problems from 2021, and we're actually doing all the problems that are multiple of 3 today. All right. Evan, do you want to take the first one?
Sounds great. All right. I see before we start that many of you have been sending messages to Chat Relay. That's great. If you want your messages to show up here, you can just send them to the person named Chat Relay in Zoom. All righty. Question 3 is, what is the value of 20 times 21 divided by 2 plus 0 plus 2 plus 1? This test happened in 2021. It makes sense. Now, this is not too hard because we can add 2 plus 2 plus 1, that's 5. And 20 divided by 5 is 4. So this is 4 times 21, also known as 84. Yeah, like Anson has said in chat. Awesome, 84. A nice warm-up arithmetic problem.
Perfect. And I think the key there is to not multiply out the whole thing. You can do 20 times 21, but by being a little patient and waiting to notice that this is 5 and that you can cancel out, it saves you some time. So be patient, look at which steps are easiest and do those first. All right, on to our second question, which is number 6. We have 5 vases here, and they each have a volume of 1 liter. So half of a liter of water is poured into each vase. In which vase is the level of water the highest? Okay, so this is a really interesting problem. What we know is that the entire thing of each one of these is going to be 1 entire liter. So right now what we need to think about is what would half a liter of water look like for each vase? So let's do some easy ones. This rectangular prism here is really easy. I think we see containers like that pretty often. If we were to fill it up with half a liter of water, it would make sense that it would be halfway, right? So I don't know why our water is green. I should put it in blue. So, nice water, and it would fill it up halfway. Which other ones would be similar? What's nice about E and C is that they're both symmetrical. So if you think about it, filling up the bottom half should be filling up the exact same as the top half, right? The bottom half is the same as the top half, which means that if I were to fill it up with half a liter, it should also go up to the halfway mark, right? And then same reasoning here for C. The bottom half should be the upper half. So that means there's no way that any of these could be the highest because there's only one answer. So the question is it A or D? And I'm seeing a lot of people saying A in chat. And the nicest thing I think is I see Anson, even Jenna and Richard, they're all saying the bottom is really skinny. And that's a great point because what's nice about the skinny part being at the bottom is that half a liter is going to go way past the halfway point because it takes less water than it normally would. Because if maybe the water line is over here, it would make sense that the thicker part at top holds the same amount as the thinner part on bottom, right? The fact that this is longer makes up for the fact that it's thinner. The opposite happens in D. So I would say that in D, the water line might be here. Obviously, it's not that important because we know this A is the highest. So that's definitely the highest. But just for thought, for D, we know that the bottom is thicker. So maybe half a liter of water would go to this much because the thicker part makes the fact that this part is skinnier makes up for it by the fact that it's longer. So in order for those two to have the same volume, that needs to be longer. So all of these three would show up at halfway. This is less than halfway. That's more than halfway. And again, the reasoning being that the bottom is skinny. Good job, guys.
Yeah, that was super fun. I also had a little fun drawing out an extreme version of A, which you can do because they don't give you specific dimension. So you can say, what if there's a teeny little straw at the bottom and then a huge pan? Well, clearly it filled just about to the top, and that's the same way of getting A. Amazing. A, amazing. Yeah. Alrighty. Now you're locking your bike because the crime rates are up. This bike lock has 4 wheels numbered with the digits 0 to 9 in that order. Very good, because it'd be a most confusing lock that did something like 0, 2, 1, 5. So 0 through 9, that's happy. Each of the 4 wheels is rotated by 180 degrees from the code shown in the first diagram to get the correct code. What is the correct code for the bike lock? Yeah, let's go to a new slide because I want to move to right. Alrighty. So you can possibly imagine spinning all of them. And one fun thing I thought is that you could, this is just like adding 5 to all of them or subtracting 5 from them. Because if you have all your tapes like this, 0, 1, 2, 3, to 9, obviously in a circle, then increasing 0 by 5, spinning 180, which is like incrementing by 5. Actually, I'm going to steal what Eddie has on his screen and make it a turnpike. Yeah, 0, 1, 2, 3, 4, 5, 6, 7, 8.
If you think about it, it's almost like if you were to take a pizza slice, not a pizza slice. If you were to slice like one of those roll cakes, right? Halfway through and you look at it this way. And it might look like this, right? So, if I keep turning it, maybe 1 will show up, maybe 2 will show up. But something along these lines.
Yeah. So if you start at 1 and you turn it 5 times, well, you'd have to turn it 5 times because they're 10 numbers. So 5 times is half of the circle. That will bring you all the way to tick, 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 6. And this makes sense because 1 plus 5 is 6. Well, what if you started at 6? Now we're actually solving the real problem. And again, turned it 5. Well, actually, the fun thing is it doesn't matter which direction you turn it. Like you can turn it around this way, or you can turn it around this way, and you'll get the same result because that's like flipping this way versus that way. It's exactly half. You have symmetry. So you can turn it 180 degrees and you'll get back to 1. Or another way of thinking about this is that 6 plus 5, when it's divided by 10, you get a remainder of 1. And that's what the first digit will go to. And actually, this is a good thing to see because options A, D, and E, they all have not 1 and distinct first digits. B and C are the only ones with 1. And what question writers like to do is sort of clone the correct answer so that if the first digit is indeed 1, they'll give you 2 options. So if you're just guessing, you might mess up. Yeah, I see lots of people are saying option B. So let's try the second number, 3. Oh yeah, 3 plus 5 is 8. So starting at 3, turning 5 times, tick, 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 you get to 8. And the only other answer that goes 1, 8 is B. So B is indeed our answer. If you wanted to go through the other two, well, 4 plus 5 is 9, and 8 plus 5 is 13. But remember, that's the same as saying that 13, what's the remainder when 13 is divided by 10? That's 3. Or you could say, maybe I turned it 180 degrees the other way. There are a lot of ways to say the same thing. Yeah, awesome. I like this explanation by Neo as well.
Cool. So a little cipher here. It's like those cryptograms where one letter goes to another letter.
Oh yeah,
But this
ciphers.
Yeah. This one's nice though because 3 goes to 8, 8 goes back to 3. You know, I also bike to school and I also use a 4-digit bike lock. So I was really scared that my combination would show up here. But I don't think any of them are close.
Oh, maybe we should check. What's your combination? We'll see how similar they are.
Maybe I'll rotate it 180 degrees.
Yeah.
I think if you were to rotate mine 80 degrees, I have to check what it is. It's gonna look like this. Wait, I got it because there's a mnemonic for my thing. I believe this is what my code looks like if you rotate it 180. Okay. But we're not putting that up there for long.
Yeah.
All right, number 12. So a jar 1/5 filled with water. So I get all the water problems. Jar 1/5 filled with water weighs 560 grams. The same jar 4/5 filled with water weighs 740 grams. What is the weight of the empty jar? Okay, so we have two components here. The jar weighs something, water weighs something, obviously. So are you sure you want to share your bike lock password to the world? Well, I'm assuming none of you guys go to my school. You'll have to double check me on that one though. All right, so I think the best way to tackle this problem is to just translate whatever the problem says into some numbers that we can understand, into some equations. Okay, so how would we do that? Since we're talking about weight, let's just set a bunch of variables that mean weight. So if a jar with 1/5 water, let's say that's 560 grams. Actually, here's what I'm going to do. We're going to call the jar J, right? So if you imagine a very rectangular jar, the jar is going to be J. And 1/5 water is W. Okay? So you can make water whatever you want, but here's what I'm going to do. So I know that 1/5 of the jar is exactly how much water is in the first equation. I'm just going to call that W because that makes my equations later pretty easy. So right now I have J plus W equals 560 grams. And then later, the second scenario says we are going up to 4/5. Now, the reason why I said, sorry, I'm going to hide chat real quick because it's getting a bit in the way. But you guys are sending in some great stuff, so keep it up. Okay, so now the water level is going to go to 4/5. But what's nice about the variable I set is instead of having to calculate with fractions and stuff, I'm just going to say we went up 4 W's, right? If I define W as 1/5 filled worth of water, now it's just 4 times as much. So now what I have is J plus 4W equals 740. Now, normally what I would say is, because we're finding the jar, let's manipulate the equations such that we eliminate W, so we get J. But honestly, in this case, if you imagine eliminating W, we'd have to multiply that by 4. And I'm kind of lazy. I don't want to multiply a 3-digit number by 4. So obviously it's going to be easier to eliminate J right away, right? So even though we're eliminating what we're looking for, oh, I missed the dot. Here, join back. All right. I'm going to subtract these two equations, in which case we get 3W equals 180 grams, right? I did that right. Cool. And so this is a nice number. 180 divided by 3 is a perfect 60, right? And what's really convenient about this is that we have a nice equation. J plus W equals 560. So because W is 60, I can now say J plus 60 equals 560. And then from there, it's pretty clear that it's going to be E, 500. And always as a double check, make sure the units line up. But this problem was pretty nice. Everything was in grams, so we don't need to worry about that. But pretty confident. E for Evan, 500 grams. That should be correct. Oops. All right.
Yeah.
Let's check it. All good?
E for Eddie. Awesome. Yeah. The second you said units, I got a little, heart quiver because I was worried. Wait, I thought that was right. Is there a units problem? Thankfully, there were no units conflicts, but always good to keep an eye out for them. They sneak up like a snake in the night to attack you, something like that. Anyway,
Yes.
yeah.
After it happens to you enough times, you're always scared that it'll happen again.
Yeah. Yes, the sketchy units are mongooses hiding. Yeah,
Okay.
you get the idea. Alrighty, but now we're building throwing stars? No, stars. We're building stars with right triangle. And 5 identical right triangles can be arranged like so to make a nice little star. And you can use more of these triangles in a different way to make a second star. But how many triangles would you need for that? Well, you could start immediately finding angles, right? We know the central angle because 5 of them make up a full circle. But maybe before we do that, let's step back a little and think, how would we even make a star with more triangles? Yeah, I see Anson has done the nice work for us, as has Anish. And they have both found that the center angle is 72. And we'll definitely use that later on. But how do we make a star using triangles, but not like this? Well, I noticed that the right triangle has 2 non-right angles, right? In this case, the bigger non-right angle goes in the middle. So I guess we could try something like that. What do you guys think? Do you think that sounds reasonable? Actually, no, I'm not sure that is reasonable. Because if we did that, well, let's just try drawing out some stars and see what happens. All right, where should I put the second triangle? Let's put a second triangle. And in a competition, I'd be just like sketching like crazy on my paper. Uh, how would I put this second triangle in? Well, I could put it. What do I want in the center? Well, in this case, I had this guy in the center, and I don't want him in the center anymore. So I guess I could put something like this. That doesn't seem like a very good star. That's actually a really ugly star. No offense or anything, but if you continue like this, you're only going to get 4 spokes. So that's not very useful. What do you guys think? Do you guys think we might be missing something incredibly obvious or some other way of making a star with these triangles? I admit that spatial visualization is not my strong point. So I'm just going to, since I can't think of a star off the bat, I'm just going to keep sketching away and maybe something will turn up. Uh, hmm. Let's see. Well, I could put in a triangle with the right angle like this. Yeah. And then I suppose I could put in another triangle like that, and then a triangle like that. Now, I don't know if that counts as a star, so maybe not. It kind of looks like a star to me, but it's also not a star because it doesn't look very regular. Oh, I see. Anish in chat is saying, make the other triangle lean on the left side of the first one. Aha, yes. Okay. So in that case, our hunch would be right that we would be using these stars. Maybe something like this. Wait, no, no. Something more like this, I guess. Yeah. So either way, the hunch that we'd be using the other little angle there is right. And if I still couldn't have found a star that worked, I would have just said, okay, let's just assume there's one that tiles it around the center angle anyway. So as people kindly found before, this angle here is 72. So the other thinner angle that would now be in the center is 18. And you'll notice that 18 times 4 is 72. So 18 times 4 is 72, which basically means that we need 4 times as many triangles to fill up the central angle. Yeah, like Nikki said in chat. And just checking, we did have 5 triangles in the first one, 1, 2, 3, 4, 5. So we would want 4 times that, or 20 in the final new second star. Yeah. And indeed, D for 20 is correct. Yay. I think in this question, it's good to, even if you can't draw the second star right away, to make an educated guess about how it's going to work and then just start going from there because, you know, you have limited time and it's really close enough.
Yeah, it's like you can't really make a star with right angles
Yeah.
because like that's not going to turn into much. So if they used 72-degree angles in this problem, who says we can't make that 71 or 70 or maybe 18, right? So you would probably just think if they use this one, maybe just do the other one, right? And it checks out. The answer choices line up. Because the angle is 1/4, I need 4 times as many triangles. And remember, the answer choices are so convenient. So it seems like it would be right. Okie doke. So let's head over to number 18. All right, not water this time, but right now we have a rectangular strip of paper with dimensions 4 by 13. And it's folded. Okay, so we're doing some folding here. So I do have paper. I could maybe invest in folding it. It's not 4 by 13. It is in fact 8 by 11. So actually, wait, this won't be long enough at all. But 2 rectangles are formed with areas P and Q here. So let's see if we can do this problem without trying to fold it in real life. And remember, we're trying to find this side length. Okay, so it's pretty clear that this is the fold line. This diagonal thing is what they folded over. In general, if you fold any paper such that it goes straight up, you're folding over some diagonal line. Because like, if I take this and I want this to be exactly up, notice how this is the crease, right? So this solid line right there is going to be our crease, which means drawing the crease line somewhere on this diagram, it might be like over here, right? So this helps us a little in knowing about exactly what's going on. And another thing special about it is we know that this is exactly 45 degrees. So that's 45 degrees. What's a special property about 45, 45, 90 triangles? What's something really nice about them that we can use to help us out? Because they don't give us much, but we can set some side lengths, and that'll definitely be nice. So what's a cool property? Isosceles. They're isosceles triangles, right? And which means that the legs are the same, right? So isosceles just means the fact that 2 of the legs are the same. So in this case, this 45-degree triangle, and by the way, the reason why that's true is because in an isosceles right triangle, for the angles to add up to 180, if this is 45 and 90, well, the other angle needs to be 45. And because that angle is 45 and that angle is 45, these two sides are the exact same. Okay, so right now what I know is that this green side and this green side are the same length. But how does it help us? We don't know what length it is, right? So if only I knew exactly how long that was. Wait a minute. Well, so we can maybe try to figure it out using what they give us. They gave us 4 and 13. So using that, what would be one of the green lengths? Perfect, Anish. So this green length is the exact same as that one. It's a rectangle, right? So these lengths are the exact same. And we know that that's 4. That's the height of the rectangle they gave us. So that's 4, which means this is also 4. And then by Pythagorean theorem, if you take a regular isosceles right triangle, if this side is 1 and that side's 1, you get 1 squared plus 1 squared equals the third side squared. So this has to be root 2. And so what we did here is just all the side lengths are multiplied by 4. So this side is multiplied by 4, that side is multiplied by 4, so we multiply the hypotenuse by 4. Actually, wait, do we need this information? We need x. Okay, actually, this isn't that important, I think. Wait, 1 second. I just don't want to do unnecessary work. Figure out what the problem is asking for. And then, okay, so we know that P equals 2Q. So right now, the fact that we have to use this last piece of information, right? We need the fact that this area, which is going to be 4 times x, right? Because this height times the length. The area here, I'll use dark blue. So this area is going to be 4x, right? And which that means this area is going to be 2x, right? Because P is double the area of Q. Okay, but because this length is 4, that means that length up here is 4. Again, it's just looking at another rectangle. So actually, here's another way to think about it. Because these two lengths are both 4, they're the same. The only way that the areas can be different is if their lengths are different, right? And because the area here is double that, that means this length is double that. And that's because these 4s are the same. So if this is 4 times x, this must be 4 times x over 2. So we know that this length over here, actually, let me draw a bracket. That's x over 2. Okay? All right, so now let's try to unfold this and see what's going on. So if you can imagine folding just the top part, it's actually really nice. So let's see what, if we were to say, take this diagram and unfold it, what it would look like. So this middle region is what got folded up here, right? So this triangle went to that triangle. And here is P, and that part is the part that went up. You can imagine, like, so the part that I'm folding over is right here. Right? Actually, I'm going to make this a solid crease. Okay, right? And this is the Q that got left. Actually, I'm kind of mirrored right now. But that's the Q, right? This is the Q, while this is the P, right? And so right now what we have is, this is the X, the P that we had. This is the X over 2. And then this we know is 4. So unfolding it, we know that this has always been 4. This diagram is getting a little cluttered. Let me see if there's a cleaner one. Yep. All right. So redrawing the crease, we know that, oh, that's not a very good 45-degree angle, but P is going to be X. And then the unfolded Q is going to be X over 2. So we have X plus 4 plus X over 2 is the whole length of the rectangle, which we know is 13. So now we just solve. X plus X over 2 is going to be 3X over 2. And then subtract 4 from both sides. That'll be 9, right? So X, take 2/3 of both sides. X is going to be 6. All right. Let's check if that's an answer choice, right? I think some of you guys are agreeing in chat. That is indeed C. So C for 7? I don't know. C and Evan gives me 7. All right. But it's 6. 6, 8, 7. 7, 8, 6? I don't know.
6. I can't think of a good pun. That's very sad.
It's hard to come up with one on the spot.
At least not one that actually goes in the correct numerical order.
Right.
I suppose 6, 8, 10 is kind of correct, but anyway, it's also 2 at a time. It's kind of ugly. Speaking of ugly, we have fractions. No, I'm just kidding. Fractions are nice, especially this fraction, because we want to double it. And to double it, we've increased the numerator by 40%. But obviously, increasing by 40% is not doubling. So we've got to decrease the denominator by some amount to actually get to double. And we want to know how much we need to decrease the denominator by. All right. So a very good thing to start is just to write our initial fraction, x over y. You could say, well, they don't specify a fraction. Let's just make it 1 over 1. I don't think it matters too much this time. And having x over y will help you not get confused later in your scratch work, mixing up how much you're increasing by and the actual original numerator and denominator. All right, so this fraction goes to 1.4x over something y. And of course, this something needs to be less than 1 because, again, that's like dividing by something less than 1 is like is the same as multiplying by something greater than 1, which will increase your fraction further. And we want this equal to 2x over 2x over y twice. We want it to double. And so now you see why they didn't give us the fraction, because it doesn't matter, it cancels. And I already see very cleverly in chat, people are noticing that we could cross multiply after canceling out x over y. So maybe I'll erase x and y temporarily. Yeah, we could cross multiply and we'd get that this something equals half of 1.4, which is 0.7. And that's exactly right. If we take 0.7 here, you'll notice that this is the same as 14 divided by 7, which is 2, which is double, which is what we want. All right. And of course, 0.7, that's 70%, right? So 70% is our answer, isn't it? Exactly. It is not. I already see people in chat. Let's see. Bharath and Emily have rightly noted that 70% is a 30% decrease. I see Math Kangaroo was nice, and they didn't include 70% as an answer choice. Yeah, but again, we want to make sure that, especially when we're dealing in percents and increases and decreases, that we're actually giving them the percent decrease, not the factor it's multiplied by, not the amount it decreased, but the percent decrease. Yeah, really nice. So now we got C 30. And it is correct. C. I see Eddie.
Okay. That was pretty good. Much better than what I was trying to do. All right. On to 24. So here we have a box that only has green, red, blue, and yellow counters. There's always at least one green counter among any 27 chosen from the box. Always at least one red among any 25 chosen. Always at least one blue among, etc., a bunch of numbers, right? With each color. So what is the largest number of counters that could be in the box? Okay. So anytime we're looking for the largest or the smallest, we're looking for the worst case scenario, or best case for you glass half full people. So we're just trying to look for an extreme. Like, so for this there's always at least one green counter among any 27 chosen from the box. Let's figure this out. So we have 27, any group of 27. So as soon as I take 27, there's at least one green. So the amount of greens is at least one. So that could mean all 27 are green. But what's the difference in 27 and 26 or 25? The worst case scenario here is if there's exactly one green counter, right? Exactly what Nish says. The worst case is that 26 of them are not green. So we'll say, what's a mixture of red, yellow, and blue? What is that? Isn't that black? All right, well, that's not very helpful for me. So we'll say that 26 of them are not green, right? Because exactly one is green. And what that does is it maximizes the amount of everything else. Because if we just say there are 27 greens, well, that's not very helpful, right? Because, in the other ones, like, first of all, it definitely can't be true, because, like, if among any 22 counters must be chosen, well, you would have to, like, take all the greens. It's almost like those sock problems, where it's like, you have 6 different pairs of socks, and how do you make sure you pick at least one pair? Well, worst case scenario is you take all the non-pairs, in which case there's 6 of them, and then no matter what the 7th one is, it's always a pair. Okay, so back to this counter problem though. We can use the same worst case scenario logic for, it says there's at least one red among any 25. So now it says for any 25 counters, red is greater than or equal to 1. Okay, so again, using worst case scenario, we can say that 24 of them are not red. Okay, and then yada yada, same thing for the rest. So 22 for here, which means 21 are not blue. And for the last one, at least one yellow among any 17. That means 16 are not yellow. Okay, so here, what we know is that at the very most, 26 of them are not green, which means I would say this. Worst case is that it's exactly 25, right? So the fact that that's not green, we would have to do that R, just basically all the other colors, R plus here. I'm going to make this easier for myself by thinking ahead. Otherwise, I'm going to be taking way too long switching all these colors. Okay, so basically, we now have 4 equations, right? So we know that at most 26 of them aren't green, and to maximize the amount of counters, we'll say that 26 of them aren't green. Okay, and so in this case, we know that red plus blue plus yellow is going to be 26, right? And in this case, blue plus yellow plus green is 24 because it's not red, right? And then in this case, red, yellow, green, because there's no blue. And in this case, no yellow, right? And so we have 4 variables, 4 equations, which means we can solve. The problem is, though, it's not very fun, right? So how would we go about doing something like this? It's really weird, right? And also, just a little note on why we can be confident on going this way is, like, for example, say that all 25 are red. If all 25 are red, there's no way that picking 16 could, or well, in the problem is 17, right? There's no way that picking 17 could guarantee me a yellow. Because what if I pick 17 reds, right? So it would make no sense to have 25 reds. In fact, this is our best option. Okie doke. So Anish did a thing where you add up all the equations. And that is actually the best trick for when you see a bunch of variables that are distributed evenly. What I mean by that is that you see every variable the same amount of times. Like this one is missing green. This equation is missing red. This equation is missing blue. This equation is missing yellow. They're all missing the exact same amount of time. Or you can say that they all show up exactly 3 times. Which means if I add them all up, I will get a very nice, like, balanced equation, right? So in this case, if I add everything up, I'll get 3 of exactly everything. 3 reds, blues, greens, yellows. Which colors have I not said? But yeah, so you're gonna get red plus blue plus yellow plus green. And then on the other hand, over here, what do you get when you add everything? So 26 plus 24 is 50, and then 21 plus 16 is 37. So that total is 50 plus 37, 87. And that's nice because 87 is divisible by 3. So divide both sides by 3, and we get that the amount of marbles total is 29. And okay, we need to solve for R, B, Y, G, but Wait, what was the question asking for again? What is the largest number of counters that could be in the box? Well, what is the number of counters? It's the total of red, blue, yellow, and green. So we actually have it right here, 29. And so I hope that that's an answer choice. It is, it's B. And honestly, I'm quite worried because it says largest, right? So how do we prove that it can't be 51 or 87 or 91? Because those are huge numbers, right? Like if 29 was the biggest number here, we would be pretty calm because we know it's true. But let's use some logic. Let's try to figure out why it might be really not true for it to be 91. So like if say the answer were 51, let's think about it. So 51 counters, there's always at least one from any 27 chosen, which means I have to be able to pick 26 bad ones and be confident that the 27th one will be green. Okay, let's imagine picking 26 from a box of 51. That would mean that after I pick 26, I have 25 counters left, and I have to be sure that that's green. So that means there's 25 greens. But if there's that many greens already, there's no way I can guarantee that I pick 17 and there will be a yellow, because what if there's 17 greens? So already 51 kind of breaks down, which means the rest will be way too big as well. So I think we're pretty confident in the fact that it's 29. All right, and we obviously don't need to check 27 because we proved that it's true for 29. So it definitely works for anything less than that as well. Cool.
Right. Nice. That was a fun problem. I especially liked the logic bit at the end. That was nice. Nice. Like a cuboid and a termite. I wouldn't normally consider termites to be nice and fluffy, but for today, they are. Our happy little termite is eating through a 3x4x5 cuboid made out of wood. Yes. Yeah, like John says, a cuboid is exactly this thing, a rectangular prism. But honestly, cuboid just sounds so much nicer than rectangular prism. It's like cuboid, cuboid, cuboid. Anyway, so it's a 3x4x5 cuboid, and our little termites eating all the way from Q to P. It's a big day. Now, the important part is that this diagonal does not intersect the edges of any small cube inside the cuboid. Although, actually, I think this problem means to say that it doesn't intersect any of the vertices. Like, it doesn't intersect here, 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 here. I would draw the inside ones, but that would get pretty messy pretty quickly. So basically that our line doesn't ever pass through, a lattice point, or really a nice, it doesn't squeeze between two cubes. Actually, it would be helpful to generalize this, or to simplify this to 2 dimensions. So I'm going to empty out a tray I have on my desk. All right. Uh, and for you nerdy people, it's a gridfinity tray. It's really nice. So, okay, focus. All righty. So this is the same as saying that our termite is eating from this vertex to this vertex. And what happens when it does that is that it'll eat all the way along here. So maybe I have a ruler. Yes, I do. Oh, it's not quite long enough, but you get the idea. This termite eats through all the way along here, and in doing so, it passes through 1, 2, 3, 4, 5, 6, 7. And you'll notice that that's kind of weird because it could be doing the same going from 1, 2, 3, 4, 5, 6, 7, as if it's going along the edges. And actually, that was the reason I thought that it was so important that the diagonal doesn't intersect any edge of the cuboid. So now drawing this, suppose we are just looking at a simple 3x2 grid that our little termite is waltzing through. Well, it'll waltz through just like this, right? And so it'll pass through these 4 squares. But each time the termite passes through a square, it's either the next square it's going to is either exactly to the right or exactly above the square it's in right now. And that's because the path does not go like this. if the path went like this, then our whole line of reasoning would break down, no pun intended, because the next square would be both up and to the right. It's like jumping over a spot. So instead, we can feel confident that each time the termite touches another square, it's either exactly one to the left, one above, or one further in for this cuboid. So basically, each time the termite enters a new square, it's only moving one unit in one direction. So it's not doing anything fancy like going up and right at the same time. It's just going up, then right, then up, then in, something like that. So really, we just need to count how many times the termite's going to do that. And so, well, we could say the termite is going to have to go to the right 4 times, go up 3 times, and go in 2 times. No. Yeah, it'll go to the right 5 times, assuming that it starts just outside here. So that thinking about that can get kind of confusing because you're going to think, oh wait, is this considered to the right, this right, or is maybe this in? What? So it'd be much more fun to just draw it out because, like we said, it's exactly the same as if the termite's going all the way along this edge, then all the way up, then all the way across. And this is because the termite's line does not pass through any of these vertexes. That's the very key point. Alrighty. So I see a lot of people in chat. This is awesome. Some are saying 5 plus 2 plus 3. Some of them are saying 5 plus 4 plus 3. So we can count. Why don't we do that? We count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the reason it's not 5 plus 4 plus 3 is because if you see over here, okay, let me move it up above chat. Right over here, the termite goes up instead of going right. So counting 5 plus 4 plus 3 would be overcounting wherever the termite turns, if you know what I mean. Yes. So like Joshua says, be careful of the repetition. Alrighty. So in this case, we would indeed choose 10 as our answer. Alrighty. Yeah, so the key part of this question was noting, oh, they tell us the diagonal does not intersect the vertex of any small cube. So that's got to be important. And then seeing that, well, if this is a 2D sort of thing, then, oh wait, that's actually quite neat because it'll pass through, 1, 2, 3, 4, 5, 6, 7. That's the same as 1, 2, 3, 4, 5, 6, 7. And finding things in the smaller 2D case allowed us to make pretty quick work of the 3D case. So the answer is indeed C. Hurrah!
That question where if we make it a diagonal and they can chew really weird directions, I'm really curious about that. If we have extra time, we should make that a question. All right. Another thing I just want to note is that what's really nice about being able to only turn left and right or whatever, like for example, using a simpler example of just a 3x3 square, all of these paths are exactly 5 blocks, right? So Evan just happened to choose the path that he used, but you can draw it however you want. As long as you get from P to Q in the fastest way possible, that should have gotten you 10 blocks.
Yeah.
All right. So moving on to our last question, I believe. So we're on number 30. That is the last question of the entire test as well. This diagram shows a quadrilateral divided into 4 smaller quadrilaterals with a common vertex K. The other labeled points divide the sides into 3 equal parts. Oh, I see. Okay, so basically, in every side here, these segments are all the same length. Where is my pen? I covered it, that's why. Okay, so for example, from the vertex, they didn't label the names of the vertices, but that is the same thing as that, it's the same thing as that, and then you would go through all around the quadrilateral. And it says the numbers indicate the areas of the corresponding small quadrilaterals. What is the area of the shaded quadrilateral? I'm assuming this is the shaded quadrilateral. Okay, all right. So they give us these 3 areas, we're trying to find the fourth. The thing that's really weird though is that These are all incredibly weird shapes. I have no idea how to find the area of. I think the only thing we can call it is a quadrilateral. And the fact is, I can't find an area of any of these. They don't say if anything's parallel. They don't say anything is. They don't give us any lengths. They don't give us any angles. So our best bet is to divide these into shapes we do know the areas of. So one way to do it may be, I always think of connecting it to the vertex. So if we start with K and maybe draw it to the vertex here, you know, that's a triangle, that's a triangle. That's something we can deal with. What's a little inconvenient though is like, imagine if I drew this vertex. So I could do this, but it's a little weird because, you know, this base is half of that entire base, right? But we could definitely try it out. So if we keep connecting vertices to K, we know that a triangle, the formula is always involving the base and the height. So we have the bases. Now we don't have the lengths, but we know how long they are relative to other segments. So for example, I know that this side is exactly twice that, right? I don't know if it's actually 2 or 1. I don't think it matters. However, we know that it's double, right? It's good to know the ratio here. For the heights, I don't think we have any clue about that. That one, we're probably just going to have to wing it. So by winging it, I mean we set a random variable because we will never know what it is. But that's all right. So we can call them like height 1, height 2, height 3, height 4. But I'm gonna do orange for the heights. And for example, this orange height here, I'm gonna call it like, I don't know, height W, because that's the closest point it is, right? And so that point is gonna be, I'll pick Q. I don't know if it's actually closer, but that's height Q. This is gonna be height S, and that's gonna be height T. Okay, now what I've done is I can, with all these really random variables, I can actually find the areas of these triangles. Okay, so I think this is going to turn into another one of those bunch of equations type. So right now, like for example, looking at this area 18 quadrilateral here, I think we're going to have to keep setting variables actually. Trying to think. I'm wondering if there's like a more convenient way to do this. Actually, I think we keep dividing. So
wait, what if you said
by that, I mean we trisect it here, right? Sorry, Evan, were you gonna say something?
Oh yeah. What if you set variables for the area of each of those individual triangles?
Yeah,
Sorry,
I
I
think
like the small and then the longer base triangle. Like A.
I was thinking of doing this. It's where what's nice about dividing it into 3 now, because earlier what I was thinking is we would have to set a variable for this base and say that that's twice that. But what's nice about dividing, you know what, I'm going to actually just erase all the things about the heights because it gets a little complicated. But please remember that we named the heights. And so, actually wait, we don't need the heights at all. I lied. Why? Because by splitting, I'm wondering if there's a bigger diagram because I'm drawing a lot of lines. There is a bigger diagram. Perfect. Okay, so what's super nice about dividing it into all 3 is the fact that because they all have the same base and the same height. So for example, right now, I'm looking at this triangle here. Right? If we called that on vertex A, I don't know, AWK, and then the bottom vertex B. So because we just marked that this base, and this base are the same because the problem says they trisected it. The problem gives us that. They all have the same base and they have the same height, right? If you can imagine, you know, I'm going to just draw this height in actually. So this triangle is base times height. This triangle is still base times height. And even KVB, this skinnier triangle, still has that as height because it's based on where the right angle is made. So in other words, these three small green triangles all have the same area. Let's call these areas A. So just a random variable, and I decided to use A. So this is going to be A, that's going to be A, that's going to be A, right? And so what's really nice about that is now I don't have to do anything about half base times height. All I know is that because these areas are the same, I'm calling it A. And so continuing this, I'll make these lines red. So if I divide this one, the side PQ up, these again all have the same bases, right? This is the same as that. Actually, I'll mark it again. So that's the same as that, same as that. And they all have the same height again. I'm not going to draw any because it's too many lines. But because they all have the same height, that means they also all have the same area. We're going to call it B, right? And so continuing it very much the same way here. So it's nice that that line's already there. But if we take this base, and that base, those are again all the same. So because they have the same height, this height, they're all going to have area C. And we wrap back around by the exact same logic, splitting this into three sides again. This base is the same as that base, is the same as this base, which means these all have area D. Okay, so we have four variables, but what's really nice is that we didn't do anything about the base or the height. How did we simplify that? By the fact that, you know, all of the A's have the same base, same height. All of the D's, same base, same height. And now we can finally use what the problem gives us. Because look at this 8, right? I'm going to slightly hide the drawing for a little bit. 8 is these two triangles, right? So this triangle that we split plus that one. In other words, the area 8 is A plus B. So right now I have A plus B equals 8. And then looking at this 18 quadrilateral, this 18 quadrilateral has A, another D, and another D. So that 18 is that consists of 2A plus 2D, and that's 18. And finally, we look at our last quadrilateral, which is 10, right? So what is that 10 quadrilateral made of? It's made of a B, another B, and two C's actually, right? Both of those C's are incorporated. So 2B plus 2C equals 10. And it's always a good habit to get an account of what we're looking for. So what are we looking for? We're looking for this question mark, which is C plus D. C plus D. So what is that equal to? Okay. So because this is all 1 times C, 1 times D, I think that we can divide these equations by 2 because they're nice like that. We can simplify. So we're going to get, after dividing these by 2, we're going to get that A plus D is 9. Sorry, A plus D is 9, and B plus C is 5. And we need exactly C plus D. So how can we manipulate these equations such that we get C plus D equals something? So we could solve the system for C and D, but what would be faster if we just straight up found C plus D. So here's my thought process. I need to get a C plus D, right? So let's take the only equation with C and the only equation with D and add them up. So if I add these two, I get A plus B plus C plus D equals 14. Well, I want C plus D. I have an extra A plus B. And A plus B is 8. It's so convenient. It works out. So I know this is 8. 8 plus C plus D equals 14. So that means C plus D has to be 6. And usually as a sanity check, what I like to do is, they didn't say it wasn't drawn to scale. So would it be reasonable if that's 8 that this would be 6? I think so. So is it an answer choice is our final question. Cross your fingers, it is. It is C. Perfect. That's another C. And I believe it is indeed 6. Cool. So really, really weird problem, but the trick was reducing the amount of variables we used. And by using triangles with the same base and the same height, that saved us a ton of work and a ton of random variables. And so at the end of the day, we only used A, B, C, D. Awesome. Evan, do you have anything else?
Yeah, this is really cool, especially symmetry. It shows up again. You guys saw the use of symmetry here, where we took total number of marbles, subtracting off each individual color. And then symmetry is actually a similar kind. A related kind of symmetry is here, where, well, although my variables were different than Eddie's, it's basically the same idea, where we had variables used in repeating ways, and that allowed us to find at least the sum of two of them, which was very good. Yeah. So that's all for these problems. Thank you guys so much for coming. And yeah, you can, if you liked it, you can see more at live.poshenlow.com/math-kangaroo. And
Yep.
again, yeah, feel free to contact support@poshenlow.com anytime. And the next level 7 to 8 live solve will be May 19th at same time, same place.
Yes.
Yeah.
We do a ton of these live solves, so
Yeah.
might not be us two next time, but a lot of other cool I guess you could call them coworkers, other friends. And so always nice to learn new stuff. We only went through multiples of 3, so you guys can always check out the other questions. You can do them with us as well.
Yeah.
Hope you guys learned something.